Hello, and welcome to Differential Equations. This is lecture 26, Matrix Exponential. Last time, we started talking about systems of first order constant coefficient ODEs and how to solve them. This time, we're going to continue talking about how to solve them by using the exponential of a matrix. So the idea here is that if you're just reasoning by analogy, since the general solution of the very simple linear equation for scalar functions, dy by dt equals a times y with a constant, is given by just e to the at times, let's say, y naught, the value of y at 0. We might expect or hope that the general solution of a vector-valued first-order equation with a constant matrix A should be e to the capital A times t times a constant vector, v naught. Okay, so our first definition is to define the exponential to be what it needs to be to make this true. So we'll just say that the exponential of a times t is the fundamental solution matrix m of t of the equation dv dt is equal to a times v, with the property that m of 0 is the identity matrix, right? So remember that a given first order linear equation for a vector valued function has many fundamental solution matrices, has infinitely many fundamental solution matrices, but you can pick one of them by declaring that at a given point it's going to be equal to the identity, right? So we define the exponential to be the fundamental solution matrix that satisfies this property. Okay, and then our second definition is to say that the exponential of this matrix is the sum of the convergent power series e to the at, so this is going to be the identity plus a times t plus a squared t squared divided by 2 factorial plus a cubed t cubed divided by 3 factorial and so on, right? So in sigma notation, the sum k goes from 0 to infinity of a to the k, t to the k divided by k factorial, right? Here, recall our convention is that t to the 0 is 1, a to the 0 is just the identity matrix, and 0 factorial is equal to 1. Right? So with this standard convention, we can write this as a single sum that starts with 0 and then just goes on to infinity. Right? And again, this is a convergent power series. So convergent in what sense? And this is a really good series. So basically, however you like. So just think about the individual entries of the matrix. Each of those is given by a sequence, and that sequence converges in the usual sense. Okay, so we can't just give two definitions of the same thing without justifying that they agree. So in this case, the key fact is that this convergence is good enough. I won't go into the details, but it's good enough that we can compute the derivative by differentiating each term. So the derivative of the exponential, right? Well, if I differentiate, I'm differentiating with respect to t. So the derivative of the identity matrix would just be 0. The derivative of every term after that, k goes from 1 to infinity, right? So if you differentiate each of these terms with respect to t, well, the a to the k stays the same. T to the k becomes k times t to the k minus 1. And then you have k factorial down here. Okay, so we can write that as the sum. K goes from 1 to infinity of a to the k. And then this k over k factorial becomes 1 over k minus 1 factorial. And then here I have t to the k minus 1. Right, and now I can introduce a different dummy variable to do the sum. Let's say L goes from 0 to infinity. So k is L plus 1. So I end up with a to the L plus 1, t to the L over L factorial. And then I could pull out an a. So I have the sum L goes from 0 to infinity, a to the L, t to the L over L factorial. And now notice that this is the same sum that defined the exponential. Okay, so we see that the exponential defined by the series satisfies the equation that we started with. And also notice that if you plug in t equal to 0 into the series, well, that just kills every term except for the first one. So you end up with the identity. So this shows that the two definitions coincide. So you can use either the fact that the usual exponential solves this differential equation, or the fact that the usual exponential has this Taylor series to extend the definition to when you're working with matrices. Okay. Now, for sufficiently simple matrices, we can compute this exponential by just explicitly summing the series. Right? But for general, matrices will need to be clever to compute it. So we'll see several examples where the matrix is simple enough that you can figure out what are the entries of a to the k, and so you can explicitly sum the series. But then we'll start talking about methods to use when you cannot say what the general term of a to the k is, which is what's happening for most matrices. But let's start with a really simple example where we can compute everything. So suppose A is the 2 by 2 matrix with entries 2, 0, 0, 3. Okay. Then if you compute A squared, you would just get 2 squared, 0, 0, 3 squared. And similarly, A to the k would just be 2 to the k, 0, 0, 3 to the k. So then if you want to compute e to the at, right, the series definition, sum k goes from 0 to infinity of t to the k, well, let's put the a on the left, a to the k, t to the k, over k factorial. So this would be the sum of 2 to the k, 0, 0, 3 to the k, times t to the k over k factorial. So this would be sum k goes from 0 to infinity of 2 to the k, t to the k over k factorial, 0, 0. Sum k goes from 0 to infinity, 3 to the k, t to the k over k factorial. And so this is e to the 2t, 0, 0, e to the 3t. Okay, if we wanted to use the first definition, then notice that for this matrix, the system of linear equations you're looking at would just be x prime equals 2x, y prime equals 3y, right, which is immediate to solve. That's x of t is equal to some constant times e to the 2t, and y of t is some constant times e to the 3t, right, which you can also express for the vector xy as multiply the matrix e to the 2t, 0, 0, e to the 3t times your vector of constants, ab. And so that shows that e to the a times t is e to the 2t, 0, 0, e to the 3t, right? Because it is a fundamental solution matrix. And if you put in t equal to 0, you get the identity. So it is the correct fundamental solution matrix, the one we want. Okay, so of course there was nothing special about the 2 and the 3 except that they were on the diagonal. So in fact, whenever A is a diagonal matrix, say A has diagonal entries A1, A2, dot, dot, dot to AN, right, and zeros everywhere else, the same arguments, right, either the power series or the fundamental solution, show that the exponential is also diagonal. E to the at is just take the elements on the diagonal of A and exponentiate them. Zeros everywhere else. Okay, so diagonal matrices are matrices that are simple enough that we can just compute the exponential using a power series. Here's another example. Suppose you have this matrix, so it's only the off-diagonal terms are there, and they're both equal to 1. So then it's quick to compute. If you square it, you get the identity matrix. If you cube it, then you get the matrix you started with. 8 to the 4th is again the identity matrix, right? And so on. So in general, we could say that a to the 2k is the identity, and a to the 2k plus 1, right? Any odd power is just the matrix A again. So that means that if you want to compute e to the at, right, this the sum k goes from 0 to infinity, a to the k, t to the k over k factorial, right? So we could write this as a sum over k even, a to the k, t to the k over k factorial, plus a sum over k odd of a to the k, t to the k over k factorial. Right? The even ones, A is just the identity, so we could put identity matrix times the sum k even, t to the k over k factorial. Plus for the odd ones, a to the k is just a itself, so 0, 1, 1, 0. Sum over k odd, t to the k over k factorial. Okay, so what are these sums equal to? Okay, well, it's not that hard to figure out. What we can do is we can use that e to the t, right, by definition, or a power series definition, is the sum k goes from 0 to infinity of t to the k over k factorial. So that's the sum over k even of t to the k over k factorial plus sum over k odd of t to the k over k factorial. On the other hand, if I started with e to the minus t, right, this would be the sum k goes from 0 to infinity of minus t to the k over k factorial, right, which would be the sum of over the k even of t to the k over k factorial minus the sum over k odd of t to the k over k factorial. And so using that, we can rewrite e to the at as the identity matrix times, so it's the sum of the even ones, right? So if I just want the sum of the even ones, what I can do is add this with this, and the odd ones will cancel, and it'll end up with twice what I'm looking for. So I can have here e to the t plus e to the minus t divided by 2, right? And then the matrix A itself times the sum of the odd ones, and same thing, if I want the odd ones, then what I could do is take this one and subtract this one. That way the even ones cancel out, and I end up with twice the sum of the odd ones. So e to the t minus e to the minus t divided by 2, right? Or if I want to put them all together, this would be e to the t plus e to the minus t divided by 2, e to the t minus e to the minus t divided by 2, e to the t minus e to the minus t divided by 2, and e to the t plus e to the minus t divided by 2. Okay, here's a similar example. Suppose A is again off diagonal, but now minus 1, 1, 0. Okay, so if you square that, you're going to get minus 1, 0, 0, minus 1, right? If you cube that, you're going to get 0, 1, minus 1, 0. raise it to the fourth power, and you get the identity matrix. And then it starts repeating, right? Because we got to the identity matrix. So we could say a to the 2j, right? Well, if you're just looking at square powers of a squared, then you get minus the identity and then the identity. And so you get again minus the identity and so on. So you get minus 1 to the 2j, 0, 0, minus 1 to the 2j, right? That's the same as saying minus 1 to the 2j times the identity. Whereas if you look at odd powers, a to the 2j plus 1, then that's minus 1 to the j times a, right? So here a cubed is just minus a, right? A to the 5th would be a again, and then a to the 7th minus a, and so on. Okay, so when I want to compute the exponential, this would be the sum k goes from 0 to infinity, a to the k, t to the k over k factorial. And so this would be, let's write down the sum of the even terms. So j goes from 0 to infinity of a to the 2j, t to the 2j over 2j factorial. And then let's put a sum for the odd terms. Let's say summing over L goes from 0 to infinity of t, a to the 2L plus 1, t to the 2L plus 1 over 2L plus 1 factorial. Okay, so when we're looking at the even terms, I have the identity matrix times minus 1 to the 2j, t to the 2j, divided by 2j factorial. Sorry, and minus 1 to the j. That was silly. This was j. Okay. Minus 1 to the j. And then for the odd terms, the sum L goes from 0 to infinity of just a times minus 1 to the L, t to the 2L plus 1 over 2L plus 1 factorial, right? And then we're in excellent shape because we recognize, so if we pull out a common factor of the identity matrix, then this is, these are the terms in the Taylor expansion of cosine, right? So here I have identity matrix times cosine t, plus and then common factor of a, and we recognize that these are the terms in the Taylor expansion of sine. So a times sine t, right? Or putting things together, we get cosine t, sine t, minus sine t, cosine t. Right? So the exponential of this matrix is given by this. Okay. Okay, so here I want to make a really important remark. What happens if you have the sum of two matrices and you're taking the exponential? So suppose you were taking the exponential of a plus b times t, right? So by definition, this is the sum k goes from 0 to infinity of a plus b to the k, t to the k over k factorial. But the important thing to notice, for example, when you do a plus b squared and you're working with matrices, then you can you can expand this out and you get a squared plus ab plus ba plus b squared. But this is not equal to a squared plus 2ab plus b squared, right? And that's because a times b is not the same as b times a when you're working with matrices, right? So when you have this a plus b to the k, you can't expand that out in terms like this, but you cannot expand it out in terms like this, like you would if you were just working with scalars instead of matrices. What's the implication? E to the a plus b times t is generally not equal to e to the a times t times e to the b times t, right? Only equal when AB is equal to BA. So only if the matrices commute is the exponential of the sum equal to the product of the exponentials. Okay, let's see that in a particular example. So let's compute another exponential. Suppose you have the matrix A given by 0, 1, 0, 0. Well, this is really easy because A squared is just 0, 0, 0, 0. And so any further power of A is equal to 0, the 0 matrix. So then computing the exponential, e to the at, well, this would just be identity plus a times t, and then stop because all of the further powers are 0. So this would just be 1t 0, 1. Right? Similarly, if b is 0, 0, 1, 0, then b to the k is equal to 0 whenever k is greater than 1. So e to the bt is identity plus b times t. So that would be 1, 0, t 0. And so notice that here, e to the a times t times e to the b times t would be 1t 0, 1 times 1, 0, t 1. So that's 1 plus t squared t 1, right? Which is not equal to e to the a plus b times t, right? The exponential of 0, 1, 1, 0 times t, right? We computed this just a moment ago. This is e to the t plus e to the minus t divided by 2, e to the t minus e to the minus t divided by 2, e to the t minus e to the minus t divided by 2, e to the t plus e to the minus t divided by 2. Right, so you see in this concrete example that the exponential of the sum is not equal to the product of the exponentials. Right, and that's because these matrices A and B do not commute. Okay, so if computing exponentials by carrying out the actual infinite series is not a reasonable approach for most matrices, what can you do? Okay, so here's an approach that works really well. Computing the exponential by diagonalization. Okay, so it works really well, but we need A to have a complete set of eigenvectors. Okay, well, suppose that A does have a complete set of eigenvectors, v1 through vn. with eigenvalues lambda 1 to lambda n, right? So here, lambda 1 is the eigenvalue corresponding to v1, and lambda n is the eigenvalue corresponding to vn, right? So there might be repetition here. That's okay. Just keep the eigenvalues corresponding to each eigenvector. And then what you do is you let U be the matrix whose columns are these eigenvectors. Right? So because this is a complete set of eigenvectors, then these are necessarily linearly independent, which means that this matrix is automatically invertible. And it turns out that the matrix A is equal to U d U inverse with D, the diagonal matrix, whose diagonal elements are exactly those eigenvalues, the eigenvalues in the same order as we put the eigenvectors in U. Okay, so that's easy to check. That's just carry out the multiplications. So if you want to check this, just move this U over to this side. You just have to check that A times U is equal to U times D. Right? But if this is really easy to compute because these are eigenvectors, and U times D is very easy to compute because D is diagonal, and you can easily see that they coincide. What's the advantage of doing this? Right? This is what's known as diagonalization. The advantage when you want to compute the exponential is that, for example, A squared would be U d U inverse squared, right? Which is the same as U d U inverse times U d U inverse, right? And U times U inverse, those cancel out, right? You get the identity matrix, but then I don't need to write the identity matrix there. So since those cancel out, I just get U times D squared times U inverse, right? And similarly, if you have A to the K, right? So that would be just U d U inverse raised to the K. So that would be U d U inverse times U d U inverse, and so on, K times U d U inverse, right? But just like in this 2 by 2 case, in this K equals 2 case, the the U inverse and the U in between two consecutive Ds will cancel, so that you just end up with U times D raised to the K times U inverse. Hence, if you want to compute the exponential, e to the at, so this would be the sum k goes from 0 to infinity of a to the k, t to the k over k factorial. But now we replace a to the k with u d U inverse to the k. Right? This computation we just did shows that u d U inverse raised to the k is u d to the k U inverse. Then we could pull out a common factor of u on the left. And U inverse on the right. And now we recognize that we have U e to the d times t U inverse. That's U, and we already know how to compute e to the dt because d is diagonal. So this is just e to the lambda 1t, e to the lambda 2t, up to e to the lambda nt on the diagonal, and zeros everywhere else. And then U inverse. Okay, so this is excellent. If you can find a complete set of eigenvectors, then you can find the exponential of the matrix. Let's do an example. Let's compute e to the e to the AT when A is 0, 1, 1, 0. By diagonalization, right? So we've already computed this exponential, but we did it by summing the series. Now let's do it by finding a complete set of eigenvectors and diagonalizing A. So to find the eigenvectors, we start with A minus lambda times the identity. So this would be minus lambda 1, 1 minus lambda. We want to put it into reducible echelon form, but I want to avoid dividing by anything involving lambda as long as I can. So I change the order of the rows, right? Then I'm almost done. I can just multiply the first row by lambda and add to the second row to end up with this. So lambda is an eigenvalue precisely when 1 minus lambda squared is equal to 0, i.e. lambda is equal to 1 or lambda is equal to minus 1. So let's consider the minus 1 first, since A plus identity is, after row operations, 1, 1, 0, 0, right, which translates to the equation x equals minus y. We find that the eigenspace for minus 1 of A is all of the xy, where x is equal to minus y is just y. So this is y times minus 1, 1, with y arbitrary. And A minus the identity is, after doing row operations, we obtain 1 minus 1, 0, 0. And so translate back to equations x equals y. We see that the 1 eigenspace is all of the vectors x, y, where x is equal to y is just y. So that's y times 1, 1. With y arbitrary. So we take as the matrix U to have first column minus 1, 1, second column 1, 1, then A is equal to U times the diagonal matrix, where I just put the eigenvalues on the diagonal in the same order that I used for the columns of U, and hence the exponential is equal to U times e to the minus t, 0, 0, e to the t, times U inverse. Right? Let's actually carry out these computations. So here we have e to the at is equal to this matrix U times this exponential e to the minus t, 0, 0, e to the t. And then the inverse. Okay, so what's the inverse of this matrix? So for a 2 by 2 matrix, it's very quick to compute the inverse, right? I'm going to divide by the determinant, right? So this would be 1 over minus 2. And then these two change places, these two change sign. So that's 1 minus 1 and minus 1 minus 1. Okay, so let's see. If I multiply out these first two matrices, I end up with minus e to the minus t, then e to the t, e to the minus t, e to the t. And then what I'm going to do is I'm going to pull out this as a 1/2. And the minus that's down here, I'm going to incorporate that into this matrix. So I'm going to have -1, 1, 1, 1. Okay, and then if you do this product, you end up with 1/2 out front, and then e to the t plus e to the minus t, e to the t minus e to the minus t, e to the t minus e to the minus t, e to the t plus e to the minus t. Okay, and notice that this matrix coincides with the exponential we had computed previously, right, by summing the series. Okay, let's do another example. Suppose we want to solve the differential equation v prime equals a times v, with a given by the matrix -4, -3, 2, 3. Okay, so I'm going to take advantage of some computations we did last time. Last time we found that the eigenspace for -3 of a is just multiples of the vector -3, 1. See arbitrary. And eigenspace 2 of a is multiples of -1/2, 1. Right? See arbitrary. So if I take U to be the matrix whose first column is -3, 1, second column -1/2, 1, then A is U times the diagonal matrix with elements -3 and 2 on the diagonal times U inverse. And so e to the a times t is equal to this matrix U times e to the -3t, 0, 0, e to the 2t times U inverse. And so e to the at would be this matrix -3, 1, -1/2, 1. Then this matrix of exponentials, e to the -3t, 0, 0, e to the 2t. And then the inverse of this matrix, right, which again is 1 over the determinant, so -5/2 in this case. And then the elements on the diagonal change places. The elements off of the diagonal change sign. If you multiply the first two matrices here, you end up with -3 e to the -3t, -1/2 e to the 2t, e to the -3t, and e to the 2t, right? Then I'm going to put this out front as 2/5, right? So I left off the minus sign, and I'm going to incorporate that minus sign into this matrix. Right, and then if we do that product, we end up with 2/5 out front. And then we end up with 3 e to the -3t -1/2 e to the 2t. Then here I get minus e to the -3t plus e to the 2t. And here I have 3/2 e to the -3t minus 3/2 e to the 2t, and then -1/2 e to the -3t plus 3 e to the 2t. Right. So, okay, you wanted to solve this equation. So the point is that e to the at is a fundamental solution matrix. Right. So we're done. The general solution to this would just be this matrix times a vector made up of constants. Okay. So next example. Again, I'm going to take advantage of computations we did last time. So suppose you wanted to solve v prime equals AV, but now A is the matrix 2, 3, minus 2, then minus 3, minus 4, 3, and minus 3, minus 3, 2. So last time, we found that the eigenvalues of A are minus 1 and 2, and we found the minus 1 eigenspace is made up of multiples of 1, 1, 0 plus multiples of 1, 0, 1, right? A and B arbitrary. And the eigenspace corresponding to 2 is made up of multiples of minus 1, minus 1, 1. So if we take U to be the matrix 1, 1, 0, 1, 0, 1, minus 1, minus 1, 1, then A is equal to U times the diagonal matrix, where I put minus 1, then minus 1, then 2, right? And otherwise zeros, times U inverse, and the exponential is U times the diagonal matrix, e to the minus t, e to the minus t, e to the 2t, and otherwise zeros, times U inverse. So e to the at would be U 1, 0, 1, 0, 1, minus 1, minus 1, 1. And then this diagonal matrix, e to the minus t, e to the minus t, e to the 2t. Then the inverse of a 3 by 3 matrix is harder to just eyeball, but you can work out what it is simply enough using Gaussian elimination. I'll just tell you what the inverse of this matrix is. Right. So if we carry out this multiplication, so multiplying these two first matrices, I end up with e to the minus t, e to the minus t, 0, e to the minus t, 0, e to the minus t, and then minus e to the 2t, minus e to the 2t, e to the 2t, right? And then this matrix remains unchanged. And if you multiply that out, we end up with e to the 2t, e to the 2t minus e to the minus t, minus e to the 2t plus e to the minus t, e to the minus t minus e to the 2t, 2 e to the minus t minus e to the 2t, and e to the 2t minus e to the minus t, and then e to the minus t minus e to the 2t, e to the minus t minus e to the 2t, and e to the 2t. And again, this is a fundamental solution matrix. So we've solved this differential equation. General solution is just multiply this by a vector of constants. Okay, so this works great as long as you can find a complete set of eigenvectors. But as we know, there are matrices that do not have complete sets of eigenvectors, right? So for example, if A is the matrix 2, 1, 0, 2, then A is deficient so we can't use diagonalization. It's diagonalization, we start by finding a complete set of eigenvectors, and this one doesn't have a complete set of eigenvectors. However, this one is easy enough to compute the exponential. Notice that I can write A as 2 times the identity matrix plus the matrix 0, 1, 0, 0. Right, let's call that matrix n. So this is 2 times the identity matrix plus n. And the identity matrix commutes with any matrix. So here I do have I times n equals n times I. Right? Both of those are just equal to n. So in this case, we do have that e to the 2i plus n times t is equal to e to the 2t times e to the nt, right? And we've already computed e to the nt. So this is just e to the 2t times 1t 0, 1, right? So e to the 2t t, e to the 2t 0, e to the 2t. Okay, so what's going on is that although this matrix is not diagonalizable, this is sort of the next best thing. It's a diagonal matrix plus something that is strictly upper triangular, right? And so this, remember, it was very easy to compute the exponential of this matrix because if you, because if you square it, you get 0, right? So it turns out that it's always possible to write a matrix, a deficient matrix, as a diagonal matrix plus a matrix that whose powers eventually give you 0 after just a few terms. In fact, if you have an n by n matrix, it's always possible to write it as a diagonal matrix plus a matrix whose nth power is equal to 0, right? Doing that, this is the next best thing to diagonalization. It's called the Jordan canonical form. So one way of finding the exponential of deficient matrices, which is very similar to diagonalizing, is finding the Jordan canonical form and then exponentiating it like that. So that's one thing you can do. There is another thing you can do, though, that doesn't require you to find the Jordan canonical form. In fact, it allows you to find the exponential of a matrix without even finding the eigenvectors. You have to find the eigenvalues, but you don't have to find the eigenvectors. That's what we'll talk about next time.